So first of all, let me congratulate both the awardees. And as you know, I will not take much of time and I will keep time for the awardees. So the awardees are, as you know, everybody, Professor S.C. Bhattacharya Award for Excellence in Pure Sciences for the year 2020 goes to Professor Raghavan B. Sunoj from Department of Chemistry, and Professor H.H. Mathur Award for Excellence in Applied Sciences 2020 goes to Professor Pushpak Bhattacharya, Department of Computer Science and Engineering. Now, let me invite and welcome Professor Anindya Datta, the head of the Department of Chemistry, to introduce Professor Sunoj. And Professor Sunoj, then you'll get around between 20 to 25 minutes to give a presentation, and remaining time we can keep for question answer session. Right. Professor Anindya. You are mute, Anindya.
All right, thanks. I don't know why I make the same mistake again and again. Thank you, Professor Atre. Good afternoon, everybody. It's indeed a pleasure and an honor to introduce my colleague and friend, Professor Raghavan Sunoj. Of course, Sunoj really needs no introduction. But still, today we are very happy that he has received this very richly deserved Professor S.C. Bhattacharya Award for Excellence in Pure Sciences from the Institute this year. This has been awarded specifically for his work on transition state models that enable in-depth understanding of several catalytic asymmetric transformations, and for developing novel predictive methods by using a combination of electronic structure computations, machine learning, and statistical methods towards accelerated catalyst discovery. In all these fields, Sunoj has really made his mark and has found his place under the sun. Is renowned across the world and respected for the research that he has done. He has been recognized by S.S. Bhatnagar Prize in Chemical Sciences in 2019, which is the highest scientific award in our country. In the institute, he has received many awards as well, but it would be opportune to say that not only is Sunoj an outstanding researcher, he excels in the field of teaching as well. These first-year students absolutely love his class, as do our final year MSc students and PhD students. They benefit a lot from the courses that he teaches. So it is no surprise that he has received the Excellence in Teaching Award several times, culminating in S.P. Sukhatme Excellence in Teaching Award in 2017. Besides, he has received Chemical Research Society of India Bronze Medal in 2013, A.V. Ramarao Research Foundation Young Scientist Award in 2012, and many other awards. He has been elected to the Fellowship of Indian Academy of Science, Bangalore 2017, and Fellowship of Royal Society of Chemistry 2015. They invited him to become the fellow there. If I go on listing Sunoj's achievements, awards, and accolades, then I'll end up giving a talk myself. But that is not why we are here today. So I stop here, and may I invite Sunoj to deliver his presentation.
Yeah.
Thank you very much, Anindya, and also thanks to Dean Arandi, Professor Milind Atre, and all others who have joined this afternoon to listen to some of what I would like to say with a somewhat attractive and perhaps provocative title, a public image of chemist and chemist image of public, and what are changing paradigms. So that would be the focus. Before I move into the actual lecture content, let me place on record my sincere appreciation for IIT Bombay for providing this wonderful oasis to carry out ideas that I have been cherishing for a long time, being able to look at chemical reactions at the atomistic level. And they have been providing us with excellent computing facility, without which none of my work would have been possible. So therefore, I must thank the Institute, not just for this award, but also for creating a research ecosystem with abundant number of good students, access to facility, and colleagues from both chemistry and other departments. I am extremely thankful to all those who have contributed to my research program here. And this is a slide which usually comes at the end, but since I have the habit of rushing through towards the last few minutes, so I thought I should acknowledge people who have been part of this group. I cannot list everyone here. 16 PhDs who have graduated over the years, and I've had the opportunity to work with some of the really outstanding integrated MSc students. Many of them are in top class universities worldwide, and of course MSc students and the current set of PhD students whose names are listed here. And many a times when I give a talk and people ask me this question, which among those penguins walking, which one is you? And my answer is, if you have that kind of naughty question, my answer is, I'm not in the figure, okay? In regards to funding, I have received funding from standard funding agencies, but the one which made the maximum difference to my research is IIT Bombay Supercomputing Facility. I should also thank some wonderful collaborators which I could work with in the recent years. Of course, I have much longer list of collaborators in the past. I work in the area of modeling and simulation, trying to solve Schrodinger equation, as you will see downstream in this talk. But eventually, any modeling, any theory that one would develop would have to be subjected to experiment. And I have this outlook that it is wonderful to have verified using appropriate experiment as what we predict using various computational methods. And some of the names which are in bold highlight, bold in blue color, they are the ones who are willing to test what we predict so far. And I hope that list will grow in the coming years. I'm extremely thankful to people who have contributed further in the growth of chemistry. Is anyone who is an administrator, can you make everyone mute? I can unmute. There is some noise disturbance. Go to participants list and mute all. Okay. All right. So let me start the actual content. The talk is organized formally. You will see a lot of informal things as we go along. Formally, chemistry everywhere, some tribute to great chemists. And the standard question, oh, chemistry is old. Yeah, it's quite old. And is there something changing in chemistry? I would touch upon some of these. These are personal views, not to be regarded as the views from the domain. And then I would talk about a little bit of research that we do and some musings on ways ahead. As one would imagine, what is the public impression about chemistry? And this gets reflected in many advertisements and in movie scenes. I was looking up the great Google, could not give me much insight because movies are typically copyrighted, so you don't get this in public domain. But if you talk about romance, for example, there is a lot of chemistry, that dialogues which come across in movies, like, oh, chemistry between us is so good. It's a standard. I think it's a very positive flavor that movies have given, both Hollywood and Bollywood. And when it comes to the common public, if you were to go around the city of Mumbai and ask a few college graduates and ask them, and they should not be from chemistry, if you ask this question, what do you think of chemistry? And they will say, oh, it's colorful. Yeah, I kind of agree. Yes, it is colorful, but we deal with a lot of colorless compounds as well. It smokes. Yeah, it produces a lot of smoke. Yes, and it explodes. It bangs. It makes a lot of sound. Yes, some are explosion and some are implosion as well. It appears similar, but the process is very different. And it is also responsible for a lot of fragrance, that be it deodorant or perfumes or whatever you use, soap, detergent, anything. A lot of fragrance comes from various compounds, both natural and man-made fragrances. It also stings. Welcome to third floor chemistry department. Occasionally, if you venture into a detour from the infill corridor, climb up to the third floor, you can sometimes really have a taste for the stink. Of quite as seen scenes in songs. You see the solid carbon dioxide floating on the floor, and one would get this heavenly wow feeling, and that is provided by a simple, relatively I think I temporarily lost that is one.
Please mute everybody.
Slides visible?
Yeah, there. Please mute everybody except Professor Sunoj. Please mute everybody.
Yes, I continue. And for us, it is for public, it gives a heavenly feel, or makes it quite interesting, cloudy. And if you don't practice it with care, chemistry can also be a easy access to the heaven as well, because it is quite adventurous, deals with a lot of explosive compounds, and one has to be trained to handle these compounds. We are quite comfortable with this hazardous symbol. Any chemical bottle that you handle in a laboratory setup, you would come across these kind of hazardous symbols. Toxic, of course, many chemicals are toxic. Some are environmentally hazardous, corrosive, and there is one symbol which is just an exclamation mark. But for a chemist, this exclamation mark has a standard protocol, and which stands for irritant. Okay, so this is a chemist's understanding about these symbols. And if you go around, ask a public, hey, what do you think of chemistry? The same old question which I was asking a few minutes ago. They will simply show this symbol, and I don't want to describe what they meant. Okay, and then we ask around further, hey, are you sure that it's an irritant? Then public will say, it's too old. Yeah, it's too old. Yes, it is. This is beautiful, old building. This is from Oxford University campus, and chemistry is old. You go just transatlantic, go to America in Boston, MIT has fancy new building, and Americans are always proud of how new their buildings are, but Europeans tend to take the other route, how old makes them happier. So chemistry has a mix of new and old. That is something that is ingrained as culture of chemists. And we stand on the shoulders of giants, and just a few photographs. And those who break the jinx that a chemist would mean that you will have long beard, right? So none of them in this picture has long beard. And people think that scientists are crazy, but just look at Madame Curie and decide for yourself, looks crazy or looks beautiful, right? So Madame Curie, and this man in the middle who wears a Gandhi-like specs is to be emphasized. Nobel Prize winner 1918 for his discovery that nitrogen from the air can be converted into ammonia en route to fertilizers. And because of abundant availability of fertilizers, the food chain had taken a very interesting turn, and there has been an increase in population of human race because of this very fundamental discovery. And this was also voted and rated as one of the best ever discovery, or most impactful discovery in humankind. That is discovery of synthesis of ammonia from nitrogen from the air. So enormous contributions have been made that needs to be acknowledged, and we are quite proud of this aspect that scientists have toiled hard to make this field a realistic field, which is old, I agree, which is rapidly evolving as we go along. It is changing times. Changing times, we are going through crisis, and what is chemist's role there? When we combine with our big cousin, of course, I could see colleagues from Chemeng. Since I am from IIT, I have the habit of saying chemical engineering very rarely, but Chemeng, with joining hands with Chemeng, where a chemist who typically does reactions in milligram, milliliters, and very rarely liters, with joining hands with chemical engineers, we have made a revolution, made a sea of change, making compounds and fertilizers or commercial products in abundance, which increased, of course, benefits and perils. But then, where are we heading to? These are the changing times, and we collectively made a lot of problems, damage to the environment, damage to water bodies. But then, the solution also has to come from chemistry and chemical engineering and environmental science and so on. Be it crop protection, pure drinking water, or medicine. All these ever-pervasive pesticide, disinfectants, and we are living in a time and age where we talk about disinfectant every day and everyone carries around a sanitizer along with them, just isopropanol, right? Isopropanol and chlorine-based disinfectants. Chemistry is touching everybody's life more than ever before in the time of pandemic. And this compound, which has transformed the life expectancy many, many decades ago, primarily during the World War time, which was a creativity under adverse conditions of World War to save life and infection. Penicillin, this is just one member of large body of antibiotics which have saved life, and it has increased life expectancy. It has made, therefore, very critical contributions in saving human race. And now, we're talking about pandemic COVID-19. No one likes it, but this gentleman and his group had discovered what is known as RT-PCR. And I don't have to describe what is RT-PCR to public as we speak. Back in 90s, this discovery was done, and the use of which is very, very evident in current times. And it appeared like a normal laboratory experiment whose value was felt few decades later, but this value was critical. There are numerous examples of this kind. And we are also preparing for the next pandemic. And there are some antivirals listed here. And the public image of when they see these compounds, they get repelled or say that, oh, chemistry is not my cup of tea. All right, that's okay. But if you look at this compound number 4 shown on the right, it is remdesivir, made some early news in the treatment of COVID, but it is debatable whether remdesivir is fully effective or not. Now, this is the title is attractive. Look at, we are preparing antivirals for the next pandemic. So therefore, it is not that chemistry is old, which we are proud of. Chemistry is taking the future in hand, future in context, and we are preparing ourselves to move forward. I have just few more minutes to talk about what we do in our laboratory. Our primary goal is to accelerate discovery, accelerate various forms of discovery of chemical reactions. We like this theoretical chemistry, which is fascinating. Our intent is to solve Schrodinger wave equation for molecules, of course, with an abundant list of approximation, not harmful approximations, but very interesting set of approximation, which will help us look at what is known as a transition state, which is a bond-breaking, bond-forming event. Go at the molecular level, understand the process, and we therefore like this equation, which is encircled, which is a truncated version of Schrodinger equation, among many other theorems which are out there. We try to apply this in chemical reaction. For us, for general public, chemical reaction is nothing but moving from one value to the other, that is from reactant value to the product value. We enjoy our journey through the hilltops. This is our transition state for a chemical process. A simple, trivial one, textbook example is shown here, which is for a substitution nucleophilic bimolecular SN2 displacement reaction. This is shown as a transition state, just to introduce the topic to you. And now we look at more complicated reactions. And those who are about to log off, please hold on. There is no need to log off. I'm not going to discuss any detail about this chemistry, except to tell you that these are hard problems to deal with. Transition states are extremely tricky to locate, and we have located that. But what is exciting here in our type of research is that we start from where experiments stop, and we give them further details so that experiments could be restarted. So this is one such example. We looked at the energetics of this reaction and predicted that there are this catalyst substrate complex, which is formed during the course of reaction, which plays a pivotal role in this chemistry, and then which was followed up by our collaborators back in 2017. They have isolated this catalyst substrate intermediate, which we have been talking about in 2015 paper, as you can see cited here, and 2017 they have verified it is indeed the case that this kind of catalyst substrate complex is isolable. So we have driven a new experiment by our research, which started from their earlier work on this topic. And this is yet another reaction where we could make some humble little predictions of what would happen if we were to vary the catalyst. So we have done enormous amount of work in this particular chemistry, which I wouldn't wish to go into the details of. We found a lot of interesting weak interactions in the transition states. These weak interactions are so weak that it wouldn't matter in a broader scale, but if you try analyzing them, and if you have the ability to harness these weak interactions, then one may be able to vary the catalytic activities, and that is what we have done. The quantity that we are interested in this problem is what is known as selectivity. We have predicted that if you were to use these variants of catalysts, which was never used before, or this set of substrates which was not used for this transformation, you may end up getting a improved selectivity of this reaction. That is indeed the case. If you compare the last two columns in this table, experimental versus predicted selectivity, you see a great agreement. And what is to be acknowledged here is that these were all computationally predicted enantiomer selectivity values and followed by experimental verification once the computed data was available. So this is a prospective validation rather than retrospective validation. We are marching along in this line of prospective validation. We collected a good number of examples from literature on a very important topic known as asymmetric hydrogenation, which are of relevance to pharma industry and so on. And we have used modern tools. I said chemistry is changing. This is one such example to illustrate how fast it is changing. It is tapping into the modern resources of artificial intelligence. And here what we have tried to do is to train a random forest algorithm among many other alternative algorithms for machine learning applications in chemistry. And we have predicted with extremely good accuracy that these could be learned using random forest algorithm. And we went ahead and predicted a few catalysts, what is known as a out-of-bag samples. And that also came out to be quite good in agreement with available experimental data. And this is the stride that we are quite excited about taking as we speak, that the combination of machine learning, statistical tools, and design of experiments, and that is the way ahead for us, because we believe that if you were to sustain cyclic chemistry or sustain with the least environmentally damaging activities in the domain of chemical science at large, we have to make accelerated technology where one would use a combination, multi-pronged approach, which would help us understand some territory of chemical reaction development. Let us compare this with a Rubik's Cube with 6 faces, 6 different colors. And if you look at once, you see 3 faces, 3 different colors. We look at the same catalytic reaction from the other side and see that whether we could learn something, let us say from multivariate linear regression, what we could learn as lead contributors, can we use a combination of computational methods, artificial intelligence, and then eventually the ultimate dream is to take it to the robotic setup to be able to discover chemical reactions in a high throughput manner. That is the direction in which we are moving towards. Yes, it is an old traditional subject. It has been transforming, had made very fundamental contribution. A few vital ones I have listed, and many more scientists have spend their lifetimes in propagating and furthering the cause of chemistry, and which has a huge connection with water, environment in the modern times. And we are collectively addressing a lot of these aspects in chemical sciences. And I'll be happy to answer questions if you have any. And that's all for today. Thank you.